Hi everybody, welcome back. So today, let's start talking about sequences. By the end of today, we should be able to give the mathematical definitions of the words sequence, geometric sequence, arithmetic sequence, and recursive sequence. We should be able to use pattern recognition to find the formula for a geometric or arithmetic sequence. We should be able to calculate the value of a term in a sequence. And we should be able to give informal definitions of convergence and divergence for a sequence and use either the definitions of those words or use good old-fashioned L'Hopital's rule to determine whether a sequence converges or diverges. Definition. And remember from yesterday that definitions are extremely important and powerful tools when it comes to writing a persuasive mathematical argument. A sequence is simply an ordered list of objects. A sequence is a list of objects in some order. Now, what these objects are, it can be almost anything. But in this class, these objects will typically be numbers. However, as you take more and more advanced math classes, you may end up dealing with things like sequences of functions, sequences of sets, sequences of vectors. But in this class, we will be focusing on an ordered list of numbers. So, for example, something like -1, +2, -4, +8, and some dots to indicate that the sequence goes on in this pattern forevermore. The first term in the sequence, in our case -1, is usually denoted by A with a subscript of 0. It's traditional most of the time, especially in computer science, to let the first number in a sequence be represented by the 0 index. The second number would be A with a subscript of 1, the third number A sub 2, the fourth number A3. So we start counting terms from 0 is traditional, especially in computer science applications. And each one of these individual numbers in the list is officially called a term. So let's look at some examples of sequences and see if we can use some pattern recognition to get an idea of what the terms in the sequence would be. For example, we have the sequence 1, 4, 7, 10, and then ... to indicate that the sequence goes on according to this pattern forevermore. So in this case, the first term would be A0 equals 1. The second term would be A1 equals 4. The third term would be called A2, and that would be 7. And the fourth term would be called A3, and that would be 10. Can you predict what the fifth term in the sequence would be? Take a moment and think about it. What do you expect? The pattern in these terms that we see as we move from one term to the next is that moving from 1 to 4, moving from 4 to 7, moving from 7 to 10, we're always increasing the value of the term by 3 units. So based on the pattern that's being presented here, I could extrapolate from that A sub 4 would be 13, A sub 5 would then be 16, and so on and so forth. Based on this pattern, I could continue to calculate terms until I reached whatever point I was interested in reaching. Now, sequences can also be described in terms of a formula like the following. If you want to know the term of the sequence A sub whatever, take that number n in the subscript and plug it into this formula, 4 to the power n. So based on that, I would say A sub 0 is equal to 4 to the power 0 is equal to 1. a sub 1 is equal to 4 to the power 1 is equal to 4. A sub 2 is equal to 4 to the power 2 is equal to 16. And so on and so forth. In fact, if I wanted to jump all the way ahead and calculate a sub 70, then I would have 4 to the power 70, whatever number that would be, some gargantuan number. Now there is another way to describe a list of numbers, and that's to use something called a recursive formula. An example of that is here below. They say the first term in the sequence, a sub 0, is equal to 0. The second term in the sequence, a sub 1, is equal to 1. But if you're dealing with any subsequent term in the sequence, anything past the first two, you can calculate the value of that term in the following way. Take the previous term, which is denoted a sub n minus 1, one step backward. Take the term before that, the previous term, two steps before the a sub n that you're working with, and add those together. So for example, if I wanted to calculate a sub 2, where n is equal to 2, then one step back, the previous term, would be n minus 1 equals 1. Two steps back, the previous term, would be n minus 2 equals 0. So if I wanted to calculate the value of a2, I could take the value of a1, one step back, and add the value of a0, two steps back, which I'm told is 1 and 0. Then, if I wanted to calculate a sub 3 can be found by summing a sub 2 with a sub 1. A sub 2 we found was the number 1, and a sub 1 we found was also the number 1. So the result of that sum would be 2. And likewise for a sub 4. We could find a sub 4 by adding a3 and a2, which we now know is 2 and 1. So the result of that would be 3. The next entry in the sequence would be 3. Do any of you recognize this particular sequence? This one's famous enough to have a name. This is called the Fibonacci sequence, where each term can be found by adding together the previous two. Now the three examples of sequences that we just examined represent three major varieties of sequences, which are each given special names. The first common variety of sequence is called an arithmetic sequence. When does a sequence deserve to be called arithmetic? The definition of that is that an arithmetic sequence is a sequence where each term can be obtained by adding a constant m to the previous term. For example, we had that sequence 1, 4, 7, 10, etc. Each term could be obtained by adding the number 3 to the term that came before. This number, m, which is added with each step, is often called the common difference. The reason being that if we take the difference of any two successive terms in the sequence, the result will be this number m. 10 minus 7 is 3, 7 minus 4 is 3, 4 minus 1 is 3, and so on. Now, the nice thing about arithmetic sequences is that they behave a lot like linear functions. Linear functions also had this property that when you increased the input by 1, the output had a constant number added to it. That number was called the slope. So if we want to find a formula for the terms in an arithmetic sequence, we can use a formula a lot like what we had when we studied linear equations back in algebra. We can use the formula that if you want the term a sub n in the sequence, all you have to do is start by taking a sub 0 and then adding on n copies of the slope. Let's test that in our given sequence. We have, for an example, 1, 4, 7, 10. And we had m equals 3. And the first term in the sequence is 1. So can we verify that a sub 2, the third term in the sequence, is equal to 2 times 3 plus 1? Yes, that formula holds true. 6 plus 1 does equal 7. Geometric sequences. Geometric sequences are basically the equivalent of exponential functions. Arithmetic sequences correspond to linear functions. Geometric sequences correspond to exponential functions. The defining feature of a geometric sequence is that each term can be found not by adding a number to the previous term, but by multiplying a number, let's call it r, by the previous term. For an example of a geometric sequence, we have the formula where the term a sub n could be found by taking 4 to the power n. First of all, this equation looks very exponential because we have 4 to some power. But not only that, when we calculated the first couple of terms in this sequence, we found that we had 1, 4, 16, etc. And every time we moved one step along this sequence, the outputs were multiplied by 4. For arithmetic sequences, the number that was added each time was called the common difference. For geometric sequences, the number that is multiplied each time is called the common ratio. Because in this case, if you take the ratio of one term to another, 16 divided by 4, 4 divided by 1, the ratio of each one of these successive terms is equal to this number 4, in general the number r, which is being multiplied each time we move through the sequence. Now, just like with arithmetic sequences, geometric sequences always have a formula that can be used to calculate terms really quickly. And just like the formula for an arithmetic sequence looked a lot like the equation for a linear function, the formula for a geometric sequence looks a lot like the formula for an exponential function. If you want to find the value of a sub n, then all you have to do is take the first term in the sequence, a sub 0, and multiply it by the common ratio to the power n. Now, the final example of a sequence that we considered was an example of a recursive sequence. A recursive sequence is a sequence where the formula for a sub n depends on previous terms in the sequence. For example, in the Fibonacci sequence, the formula for a sub n depended on the sum of the previous term a sub n minus 1, one step back in the sequence, and the term a sub n minus 2, two steps back in the sequence. For another quick example of a recursively defined sequence, I could just make up basically whatever I wanted. I could say, for example, all right, let's start with a naught equals 2, and then for every larger index n, let's say that we'll get that term by squaring the one that came before. This would be another example of a recursively defined sequence. A1 would be a naught squared, 2 squared, 4. So A2 would be 4 squared, 16. So A3 would be 16 squared, 256, and so on and so forth, for as long as you wanted to do these calculations. Now, a quick word of warning, in particular about the formulas that are used here in green for arithmetic sequences and for geometric sequences. These formulas are all based on the convention that A naught is the first term. So if you have a sequence that's provided to you by someone who is not familiar with the CS world, you may have to make some adjustments in order to find the correct formula based on what they have decided the first term will be. As a quick example, suppose that someone has the sequence, you have the term 2, and then you have the term 5, and then you have the term 8 and 11, and so on. But the question tells you that the first term in the sequence is what they're thinking of as a sub 1. So they must be thinking of 5 as a sub 2, and 8 as a sub 3, and 11 as a sub 4. We would have to figure out what the term a sub 0 would be based on this pattern. Now, this sequence is arithmetic because every time we move from one number to the next, we're adding 3 to the result. So the question is, based on that pattern, what number would precede A1 equals 2? In that case, I would have to subtract 3 to go one step backward to deduce that A naught is equal to minus 1. And from that, now that I know what A naught is, I can find a formula for this sequence. A sub n is equal to n times the common difference plus the A naught, which is minus 1. So be careful about that. Make sure that you're reading the question carefully so that you know for sure whether the first number that you are given corresponds to A naught or whether it corresponds to A1. If you are not given the value of A naught, then you will need to calculate the value of A naught before you are able to use the formulas in green given above. Let's get some more practice with this idea. Exercise, let's determine whether each of the following series is arithmetic, geometric, or neither. Then come up with a formula for the nth term in the sequence. That is a non-recursive formula for a sub n. So my convention will always be that the first term in the sequence corresponds to a sub 0. So based on my convention, which comes from the CS world, in the first sequence, A0 would be 2, the first number given, A1 would be 7, A2 would be 12, and so on. Now looking at the pattern that is showing up with the terms in this sequence, I can see that they are increasing by 5 each time we move from one number to the next. So this sequence is arithmetic with a common difference, or a slope if you prefer, of m equals 5. So now we have m equals 5, which is basically the slope. We have 2, which is the first number in the sequence. And so the formula can be found by taking m5, multiplying it by whatever n you're working with, and adding the first number in the sequence. And we can confirm, for example, we can check that if n is equal to 2, we get 5 times 2, which is indeed 12. That matches the pattern in our sequence. 1, 1, 2, 6, 24, and 120. First, I'm going to check if the sequence is arithmetic. But I can tell that that's definitely not the case, because moving from 1 to 1 involves adding nothing, but moving from 1 to 2 involves adding 1. So there's already a discrepancy here, so this sequence definitely cannot be arithmetic. To be arithmetic, you have to add exactly the same amount with each step. So next, let me check if this sequence is geometric. Now, moving from 1 to 1 involves multiplying by 1. Moving from 1 to 2, however, involves multiplying by 2. So the terms in this sequence do not have a common ratio, and as a result, this sequence is not geometric either. So that means that finding a formula for the nth term in this sequence is going to be a little bit challenging, because we won't be able to rely on the green formula for arithmetic sequences or on the formula that we had for geometric sequences. Instead, I'm going to introduce something that may be unfamiliar to you at this point, which is the so-called factorial. The notation is the number n with an exclamation point after it. And this is read out loud as n factorial. We will be using the factorial substantially as we move through this chapter of material. N factorial, what this is telling you to do is to take all the numbers from n down to 1 and multiply them all together. Multiply together all the whole numbers between n and 1. For example, if I wanted to calculate 4 factorial, then I would take 4, and now I would begin to count down. 4, 3, 2, 1, and I would take all of those numbers and multiply them together. Result, 24. Now, a weirdo little convention, just something that helps our formulas and stuff to work out nicely, is that 0 factorial is equal to 1. There is no good reason for this, really, except that it's just necessary to make our formulas compact and nice. So this sequence that we have been given, 0 factorial is equal to 1, 1 factorial is also equal to 1, 2 factorial is equal to 1 times 2, so that's equal to 2. 3 factorial is 3 times 2 times 1, so that gives us the 6. We calculated earlier that 4 factorial was 24, and then you can also calculate that 5 factorial, 5, 4, 3, 2, 1, is that 120. So this is the sequence corresponding to the factorial. Neither arithmetic nor geometric, but we will be seeing it pretty often as we go forward in this chapter. Let's check out the next example. We have the sequence 2, minus 1, positive 1/2, negative 1/4, positive 1/8. Now, I think this is definitely not going to be an arithmetic sequence, because moving from 2 to minus 1 involves adding a negative number plus negative 3, but moving from 1 to positive half involves adding a positive number. So this is definitely not arithmetic because there is no common difference. But let's see if we can figure out whether it's geometric. So let me calculate a few of these ratios to see if we can find a common ratio. If I calculate the ratio of minus 1 to 2, then the result of that is 1/2, negative 1/2. We don't even have to do any calculations there. If I calculate the ratio of 1/2 to minus 1, then the result of that after simplification is negative 1/2 again. If I calculate the ratio of negative 1/4 to the previous term, positive 1/2, then that is also equal to negative 1/2, and so on and so forth, all the way down the line. In other words, every time I move from one term in the sequence to the next, I have to multiply by the number negative 1/2. So the sequence is geometric with a common ratio of r equals minus 1/2. And with my convention that a0 is the first number in the sequence, a0 would be 2. Therefore, using the formula, a sub n can be calculated by taking the first number in the sequence and multiplying it by the common ratio n times. Now let's just check. We had a0 equals 2, which means that a1, the next term, would be minus 1. a2, the term after that, would be equal to positive 1/2. So let's try plugging in n equals 2, for example, to this formula, just to make sure that we have it right. A sub 2 is equal to 2 times negative 1/2 to the power n equals 2. If we simplify that, we get 2 times 1/4, which gives us indeed 1/2, which matches what is in our sequence, so this formula is correct and can be used to calculate terms in the sequence all the way off as large an n as we want to. Now that we have talked about sequences, what they are, what they look like, how to calculate the terms in the sequence, and how to find formulas for the terms in the sequence, we can now go ahead and talk about when a sequence converges and when a sequence diverges. Now, you've heard the terms converge and diverge before, when dealing in particular with integrals, so-called improper integrals, which had an infinity in there somewhere. And this is a very similar concept. It's about whether or not your sequence gets closer to a number or whether it's doing something else. Now, just as a note, there are occasions in the class where we're going to have to be a little bit more informal with our definitions and describe them in more plain colloquial English. Because sometimes the real definition of the term is just more complicated than we really have time to cover in the course. And so what I will be giving you right now is an informal definition of the word converge and an informal definition of the word diverge for a sequence. Technically, we would not be able to use these words in an airtight argument that the skeptic would be unable to argue with, but they're going to have to do for right now, just because the formal definition, the real definition, is beyond the scope of the class. So here is an informal definition for the term converge. A sequence converges if the terms in the sequence approach, or in other words, get closer to some fixed number, let's call it L, as n gets infinitely large. In other words, as you move through the sequence, those terms begin to converge on, begin to get closer to some fixed number. This number L is called the limit of the sequence. Now we also have the word diverge, and diverge is simply shorthand for the sequence does not converge. Now in practice, this is almost identical to when we were doing limits at infinity of functions. A function approached the limit L if its graph got closer and closer to L as you went out to the far right of the graph, and x went to infinity. Here we have a limit of L if the terms in the sequence approach some number as n goes to infinity. Let's see if we can figure out whether the following sequences converge or diverge. And we're just going to give an informal argument here, because all we have is an informal definition of convergence and divergence. If they do converge, let's also see if we can figure out what number they are converging to. What is the limit? First up, we have a geometric sequence with a common ratio of 2. Let's see if we can get a hold of what is happening to this sequence as n starts to get large. As n gets large, then we are raising the number 2 to larger and larger powers. So 2 to the n starts to get very, very large. And it approaches infinity. So the terms of this sequence are approaching not a number, they are approaching positive infinity. Because the terms in this sequence are not approaching some fixed number, this sequence diverges. Infinity is not a number. The terms in the sequence are growing without any limit at all. So I would conclude that the sequence diverges. The next sequence is described to us with a formula that contains the factorial. A sub n is equal to 1 over n factorial. Now let's write out a couple of terms in this sequence, and let's see if we can get a read on what the sequence is doing. A sub 0, for example, is equal to 1 over 0 factorial. And by convention, by agreement, 0 factorial is equal to 1. So a sub 0 is equal to 1. A sub 1 is equal to 1 over 1 factorial. 1 factorial is just 1. So a1 is equal to 1. No change so far. But let's do a sub 2. A sub 2 is equal to 1 over 2 factorial. 2 factorial is equal to 2, so that's 1/2. A3, 1 over 3 factorial, is 1 over 3 to 1, 1/6. And correspondingly, A4 is 1 over 24, A5 is 1 over 120, and so on. So with each step, we are taking the number 1 and we are dividing it by a quantity which seems to be growing pretty rapidly. So the terms in this sequence are getting very small pretty quickly. And as n gets larger and larger, and we divide by more and more, then the result will get closer and closer to 0 as n gets large. N factorial gets very large. So 1 over n factorial goes toward 0. As a result, the terms in this sequence are approaching some fixed number. In this case, the fixed number is 0. So the sequence converges and the limit is 0. Let's try the next one. We have a sub n is equal to -1 to the power n. Let's calculate a few terms of this sequence and see if we can say anything. A sub 0 is equal to -1 to the power 0, which is +1. A1 is equal to -1. And correspondingly, A2 is +1, A3 is -1 again, and A4 is +1 again. And so on and so forth. This sequence will continuously flip-flop between +1 and -1. Because this sequence is always flip-flopping between these two numbers, the sequence is never getting closer to any fixed limit. So this, as n gets large, an is not approaching anything. It keeps bouncing between these two extremes. And because of that, this sequence does not converge. This sequence diverges. As a final example, let's consider the sequence where a sub n is equal to 1 minus cosine of n all over n. Now notice that we cannot actually divide by 0 in a fraction. Since we can't divide by 0, a sub 0 is undefined. So we'll have to swap to the convention that a sub 1 will be the first term. Now cosine is a pretty unique function because no matter what you do, the value of cosine will always be trapped between -1 and 1. Which means if you go in and divide cosine by something, in particular if you divide cosine by n, then the output of that will always be squeezed between -1 over n and +1 over n. You probably did an argument like this when you used the squeeze theorem in Calculus 1. Now, as n gets large, then 1 over n and -1 over n both go towards 0 because you're dividing 1 by a steadily increasing number. Which means that cosine n over n, who is trapped between these two functions, must also be going to 0. Now let's look back at the actual formula for the sequence. A sub n was equal to 1 minus cosine n over n. Now if the cosine n over n part is going to 0, then all that will be left eventually is this 1 in the front. So an is approaching +1, so this sequence converges. To a limit of 1. Now you have potentially noticed that the arguments that we have done throughout this page have been very, very similar to the arguments that you used to calculate limits in Calculus 1, when you were calculating the limit as x goes to infinity of a function f of x. And yes, this is exactly right. We basically have just been calculating good old-fashioned limits using the same techniques that we used in Calc 1, the same thought processes. Now in Calculus 1, we also had a rule that could be used to help us to determine the limit of something like a fraction. And that same rule can be used here, the so-called L'Hopital's rule. So let's express L'Hopital's rule for sequences. And this is our very first officially stated theorem for the class. So as I am writing this theorem, I want you to think about what is the hypothesis of this theorem and what is the conclusion of this theorem. What condition or conditions have to be true in order for the theorem to be used? And then, which condition is true as a result of applying the theorem? Okay, so let us suppose that we have two sequences. I'm going to call those sequences A sub n and B sub n. And let's suppose that we know the formulas for both these sequences. The formula for the first sequence I'll just call F for short. The formula for the second sequence I'll just call G for short. If the following condition is satisfied, if you have either that the limit as n goes to infinity of the first formula and the second formula are both 0, or alternatively, if both of these limits are equal to infinity, then you can calculate the limit of the ratio by looking at the limit of the derivatives. F prime and G prime. So, what are our hypotheses? Our hypotheses are that, first of all, we have some sequences with formulas, and the second thing that must be true in order to use L'Hopital's rule is that the limit of the two sequences, they must both go to 0 or they must both go to infinity. If that is true, then you have the ability to calculate the limit of a third sequence, which is the fraction with an on the top and bn on the bottom. To note, this is basically exactly the same as L'Hopital's rule from Calculus 1. So let's try and use L'Hopital's rule to calculate the limits of the following sequences. And let's try and write a formal argument. Let's try and convince the skeptic that our answer is correct. We have, for example, a sub n, whose formula is given by n over natural log of n. So the formula that we are trying to find the limit for is equal to a fraction, n at the top, natural log of n at the bottom. Now, as n goes to infinity, both the numerator, n, and the denominator, natural log of n, go to infinity. Which means that L'Hopital's rule is unlocked. We have satisfied the condition, the hypothesis condition of L'Hopital's rule, because we have that the limit of the numerator and the limit of the denominator are both equal to positive infinity. And that means that I can calculate the limit of a sub n of this fraction by calculating the limit of what I would get if I took the derivative of the top and the bottom. Now, if I take the derivative of the function f of n is equal to n, then by power rule, I will just get the number 1. Treating n as the input variable. N is behaving like x here. And if I take the derivative of g sub n equals natural log, the denominator, then by the formula for the derivative of natural log, I get 1 over n. So 1 divided by 1 over n is equal to n, which approaches positive infinity as n gets large. Therefore, our original sequence is doing exactly the same thing. And the original sequence diverges. Let's do another slightly less straightforward example of L'Hopital's rule, where we have a sub n equals the nth root of n. Very famous. So I'm going to nickname the limit of this sequence by capital L. I have no idea what it is or even if it exists, but I'm just going to put a placeholder letter there. Now I'm going to think about the nth root of n as an exponent of 1 over n. And what I'm going to do is I'm going to apply the natural log to both sides. The reason being that the natural log allows me to pull stuff out of an exponent and turn it into a constant multiple. Now the natural log of n to the power 1 over n, you can take that exponent of 1 over n, pull it to the front. So that gives us 1 over n times natural log of n, which is equal to natural log of n over n. Okay, so applying that was the left-hand side. So we have the limit as n goes to infinity. And what we now know is natural log of n over n. And if we apply the natural log to the right side, we get the natural log of the limit. Now, just as in the previous argument, both natural log of n and n are going to infinity. So L'Hopital's rule is unlocked. And we can calculate the limit of the derivatives. Now, as n goes to infinity, 1 over n is going toward 0. So the left-hand side is approaching 0, and that 0 is equal to the natural log of the limit. Finally, if I wanted to know what the limit itself was equal to, I can get rid of natural log with its natural enemy, the exponential function. Natural log and e cancel each other out, and L, the limit, is equal to e to the power 0 is equal to 1. So the sequence converges to 1. So this concludes today's material. We talked about what a sequence is, and we talked about two common varieties of sequences, arithmetic and geometric, and we talked about their formulas. We talked about recursive sequences and the extremely famous Fibonacci sequence. We talked about convergence and divergence of sequences and how to determine whether a sequence converges or diverges using, for the most part, the thought processes of Calculus 1. Things like squeeze theorem, things like just inspection, and things like L'Hopital's rule.